Okay, it's time to have a look at an application. So for this application, we're going to have a sequence of IID variables that are what we call Bernoulli variables. So the probability of xj being 1 is the same as the probability of xj being -1, and that's 1/2. Typically something like a coin toss. Now we define Sn to be the sum of these variables. Xj equal 1 to n, and we define Fn to be the filtration, to be the sigma algebra generated by the first n of the IID variables, and that forms obviously a filtration. We initialize it with F0 equal the trivial sigma algebra, and we initialize Sn with S0 equal to 0. Now, Sn is the accumulated wealth. If you think of xj as your gain or loss in a fair game with two possible outcomes, you can also visualize Sn as what's called a random walk. You start at 0 and you move either to the right or to the left with probability 1/2, and Sn is wherever you might have arrived at time n. And the question we're going to ask is, what is the probability that Sn eventually goes above a certain value a before it goes below a certain value minus b? Right, so this is about properties of random walk. This is all sort of applications in physics and biology in particular. This is the absolute simplest example, and you're trying to understand the exit times of that random walk, at what time it exits a certain region. If you want to keep this application in mind where Sn is your accumulated wealth, well, and the question is at which time should you stop with having gain A, and what is the probability that you stop with a gain of A before you've lost B. Right, so we'll see that the theorems we've seen so far allow us to get a very neat and reasonably simple, given the theorems that we now have, answer to this question, which would be relatively difficult to treat using basic probability, although it sounds like very much a basic probability question. So in order to answer this question, we're going to introduce a stopping time, which is the time at which you exit the interval minus b to a, either through b or through a. So first of all, let's make things precise. I have a and b, two natural numbers, non-zero, and I'm going to define a stopping time, tau, in the following way. It's going to be the minimum, two possibilities. It's going to be the minimum of the ends such that Sn of omega is A or Sn of omega is minus B. That's in the situation where you do exit the interval, or I'm going to define it to be infinity, so that's if there exists an n such that Sn of omega is A or B, and then infinity if not. So if you don't exit the interval, then the exit time is infinite, and if you do exit the interval, it's the first time at which you've reached the boundary A or minus B. Now, I want to show that this is a stopping time, so I give myself a natural number and I consider the event tau smaller than n, smaller or equal to n. Now, what's that interval? So that means you've exited at a time smaller or equal to n. So either that time was 1 or 2 or 3, anything before n. So this set is really the union for j equal 1 to n of the set tau equal to j. And what does that mean? That tau is equal to j. That means that s of j is a or s of j is minus b. So this is the union j equal 1 to n of sj minus 1 of just the point A union sj minus 1 of the point B. But sj is measurable, it's fj measurable, so sj minus 1 of A, well, that's actually a single point, so I should do that. Sj of the singleton here is certainly an element of fj, and sj minus 1 of b is an element of fj. That's because sj is fj measurable, and now I'm doing a union, and fj is included in fn, and now I'm doing a finite union of elements of fn, therefore I belong to fn. So tau is a stopping time with respect to the filtration, fn. Okay, so I have a stopping time. What do I get from theorem 2.1.2? I get that the stopped martingale Sn minimum tau is also a martingale with respect to that same filtration. Right. But being a martingale tells me that the expectation for any n in n, the expectation of Sn minimum tau is going to have to be the same as the conditional expectation of Sn minimum tau given something, let's say given Fn minus 1. But this conditional expectation has to be Sn minus 1, right? Minimum tau, because Sn minimum tau is a martingale. That's the martingale property, and the first one was one of the properties of conditional expectation. Now I can repeat the argument and say that the expectation of Sn minus 1 minimum tau is the expectation of the conditional expectation of this variable given Fn minus 2, and you could repeat that until you reach the expectation of S0 minimum tau, and while 0 minimum tau is just 0, so what you get here is the expectation of S naught, but S naught is 0. So what have we got? We've got that the expectation of Sn minimum tau has to be 0 for every n. Now notice that S of tau, which is the variable that sends omega to S tau of omega, by the way, you need to interpret that correctly, is equal to what? So, well, there's two possibilities. Either when you exit through A, or you exit through minus B at an exit time tau. So you can be either equal to A in the situation where S of tau is A, or you can be equal to minus B in the situation of S of tau being minus B. So that's interesting, because that tells me that A times the probability of exiting through A minus B times the probability of exiting to minus B, which is really 1 minus the probability of exiting through A, is equal to the expectation of S tau, right? Taking expectation on both sides. So if you rearrange that a little bit, you get that A plus B times the probability of exiting through A is equal to B plus the expectation of S of tau. Now, I expect, excuse the pun, the expectation of S of tau to be 0, because the expectation of n minimum tau is 0 for all n. So sending n to infinity should give me that this expectation is 0. And if I can prove this, then I get that the probability of exiting through A rather than minus B, and the vocabulary of my application of making A dollars before I lose B dollars is exactly B divided by A plus B. Neat little formula. And it's nice in this formula to run some reality checks, right? What happens if B is equal to A? If B is equal to A, then this number is 1/2, and that makes sense, right? I mean, if the interval is symmetric around 0, there should be a probability 1/2 to exit to the right as opposed to exiting to the left. On the other hand, if I send B to infinity, then this probability tends to 1. Okay, so I'm surely exiting a finite interval before I go to minus infinity. That's also very reasonable. And the closer B is to 0, the smaller this probability get. That also makes sense because I'm starting at 0. So if A is very far away from me and B is very close from me, then I'm much more likely to exit through minus B. Okay, so that looks right, and that's a very neat formula for computing the probability of exiting through one side of the interval rather than the other. But it relies on me being able to establish that the expectation of S tau is 0. So what do we need to show here? We need to show that the expectation of S of tau is the limit of the expectation of Sn minimum tau as n goes to infinity. Right, so let's prove this. Okay, so there's 2 steps to this claim that we need to prove. The first is to prove an almost sure convergence, and the second one is to have a domination that will allow us to apply the dominated convergence theorem. Now, to get the almost sure convergence, let us first look at what happens whenever tau is finite. So when tau is finite at a point omega, whatever that point may be in your probability space, this sequence eventually stabilizes and is equal to S tau of omega whenever n is greater or equal than tau of omega, because then the minimum is exactly tau of omega. So if the sequence is eventually constant, that means that its limit, well, at such a point omega, is necessarily equal to S tau of omega. All right, so whenever tau is finite, then the limit of Sn minimum tau is S of tau. Okay, the question is, does that mean that I have convergence almost surely? Well, yes, because there's an exercise in the note, not in the notes, in the worksheet, that gets you to prove for this particular example the fact that the probability of tau being finite is 1. Right, so the stopping time is finite almost surely, and therefore Sn minimum tau tends to S of tau almost surely, because it does on a set of probability 1. Right, so I have almost sure convergence. I want to upgrade that to get the convergence of the expectation, or put in a different way, to be able to exchange this limit and this expectation. The dominated convergence theorem is a very good way to do that. And why do I have domination? Well, if I look at Sn minimum tau for any n, that variable actually is bounded, because either you're still in the interval minus ba, or you've exited at S of tau, or you're equal to S of tau, and then you're equal to either a or minus b. So one thing for sure is that this variable stays between minus b and a, so it's smaller than the maximum of A and B. So I have something that is in L infinity, and it's controlled pointwise by this constant, and this constant is in L1. So, right, the map that sends omega to the constant maximum of AB is in L1, and that's my dominating function. So by dominated convergence, what do I get? I get that the expectation of Sn minimum tau tends to the expectation of S of tau as n goes to infinity, and that gives me that the expectation of S of tau is 0. And I've proven this neat little property about the probability of exiting through the right before you exit through the left. Right, and don't forget to do this exercise in your worksheet. That is a key part of the argument. Right, now in the exercise you will prove two things. You will prove not only that, but you will also prove that the expected value of this tau is also finite. So this variable tau is finite almost surely, and in fact is in L1, and that's a consequence of the fact that you're going to get a very quickly decaying estimate on the probability that tau is greater than j. Let's say you would have a exponentially decaying tails for that variable. So you'll see that in the worksheet. I'm going to now use this fact that I know that the expectation is finite to actually compute it. Now, so that will tell us not just what the probability is that we finish the game by being rich rather than being broke, but it will also tell us how long we should expect to wait before that happens, before we exit through A or minus B. So in order to do that, we're going to consider the Martingale Mn that is defined as Sn squared minus n times the variance of my xj, which is 1. So I'm defining this for all n, and I have by the third example that Mn is a martingale with respect to the filtration induced by the IID variable, because the expectation of xj squared is 1 for all j equal 1, 2. Well, actually for all j. I haven't fixed my n. All right, so I have a martingale. So again, I can stop it using my stopping time, and Mn minimum tau will be a martingale again. Right, now what does that give me? I can use the exact same reasoning as I did on Sn, and I would get that this expectation is equal to the expectation of the conditional expectation given Fn minus 1, and I can repeat that, and I get that the expectation is the same as the expectation of M0. That's a general fact about martingales. They have constant expectations. So the expectation of Mn minimum tau is 0. Can I conclude from there that the expectation of M of tau is 0, just like I did before? Well, the probability of tau being finite is 1. So Mn minimum tau converges to M of tau almost surely. It's the exact same argument as before. What about domination? Well, Mn minimum tau for any n and for every omega. What is that? Well, it is Sn of omega minimum tau of omega squared minus, so I'm just going to use triangle inequality and say that this is smaller than plus the minimum of n tau of omega. So this is certainly smaller Now Sn minimum tau is smaller than the maximum of A and B, so this is smaller than the maximum of A squared and B squared, and this minimum of n and tau is, well, certainly smaller than tau. But tau is in N1. That's part of the exercise that I've left for you. And this constant random variable is also in N1 because constants are in N1. So by dominated convergence, I get that the expectation of m tau has to be the limit of the expectation of m of n minimum tau, but we've seen that all of those are 0. So the expectation of m of tau has to be 0. Now that has a neat consequence. Okay, so 0 is the expected value of m of tau. But what is the expected value of m of tau? It's the expected value of s of tau squared minus the expected value of tau. Therefore, the expected exit time for this interval minus BA is the same as the expected value of s of tau squared. But what is s of tau squared? Well, it is either a squared when s of tau happens to be a, so when you exit to a, and when you exit to b, it is b squared. Oh, sorry, when you exit to minus b. Now we've computed this probability before. The first one is b divided by a plus b, and the second one, well, it's 1 minus that, so it is a divided by a plus b. So you can factor out AB and you get AB times A plus B divided by A plus B. So you get AB. And that's our next neat formula. We've computed the expected value of the exit time. So when you have a standard random walk like this, you start at 0 and you move left to right with probability 1/2, and you wonder when you're going to escape a certain interval of the form minus BA. Well, you expect to exit this interval in A times B unit of times, and the probability that you do it from the right before you do it from the left is B divided by A plus B. And of course, reciprocally, the probability that you do it from the left rather than the right is A divided by A plus B. So we got all this information out of correctly applying the stopped Martingale theorem, or this particular case of the theorem about Martingale transforms still being Martingale. The trick was to choose the Martingale appropriately, right? For this first set of results, we chose the Martingale that was the sum of the variables, so the random walk itself, which was a very natural choice. Here, this is already a little trickier. The right choice was the Martingale defined by Sn squared minus n, so the one that was in our third example of Martingales. And that is a very general strategy to solve all sorts of questions in probability theory. Just manufacture an appropriate Martingale and an appropriate stopping time and reinterpret your question as a question about the behavior of the stopped Martingale.